Well, hello there, folks. I hope you're doing well. Today, we're going to be talking about probably the most important rule of derivatives, and it's a pretty big section. It's a bit of a doozy. Things get a little ridiculous, but it's important that we do it. That rule is the chain rule. So if you want to follow along in your textbook, this is found on starting on page 96. So this is section or chapter 2.6, the chain rule. So up until now, we've found lots of different ways to find the derivative or differentiate a variety of functions. However, we have not yet learned how to differentiate functions that are combined. That is, for example, the function f of g of x kind of thing, like our old fog, if you remember back to Math 30-1. We did do two special cases where we had a function squared and a function cubed, where we would exploit the rules of our perfect squares and our perfect cubes and our difference of squares and stuff like that. But now, after today, you'll be able to differentiate anything, even if it's not just squared or cubed. If it's the power of 8, power of 20, whatever, you will have the skills to do it. So let's just start off right at the beginning here. Just with the theory. So, if we were given, for example, a function f. Sorry, having some issues with my toy right now. Let me put that right there. The function big F is equal to, so f of x is equal to the square root of 2x squared plus 3. Right now, you don't have the skills to deal with this, but we can look at this as a composite function. We can say, well, let y equal the function little f of u, which is equal to the square root of u, and let u equal 2x squared plus 3. So two functions there, f of u and u. Then we could also say u is equal to the function g of x. So now we have a composite function. If we have f of u, or the square root of u, is equal to, f of u, and we have u is equal to g of x, that's the same as y being equal to the f of the g of the x. Or perhaps more familiar, fog. This is usually a little smaller, but there we are. So this is what we're going to be dealing with here. The chain rule lets us know, and there's proof, of course, in the book, but we're not going to do the proof at all, that for the function y with respect to x, if we break it apart as a composite function, the derivative of y with respect to, in our case, we use the letter u, so u multiplied the derivative of u with respect to x will give us the derivative of the original function. So in other words, for this example here, so the derivative with respect to x of our function f is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x, or, using the numbers that we have, the derivative with respect to u of the function the square root of u multiplied by the derivative with respect to x of the function u, which is 2x squared plus 3. And we'll be doing this example. This is example number 1. But before we do that, I will throw up one more example. Or I'll just rewrite what our rules are for the chain rule. So the rules, the one that we did first, the Leibniz notation, which is probably easier to remember, dy by dx is equal to dy by du multiplied by du by dx. We're just using simple cancellation techniques to throw in an intermediate step, much as we do when we want to, for example, rationalize a denominator, something like that. We just exploit the fact that anything divided by itself is equal to 1 and can be thrown in any time into basically any equation. If we want a slightly more complex version of the chain rule, which is also okay to use, the derivative with respect to x of the composite function f of g of x is equal to the derivative of f of g at x multiplied by the derivative of g at x, or g of x. So once again, I would recommend using the Leibniz notation for the chain rule. So going back to our original question there. Example number 1. Find f prime x, the derivative of big F x, where the original function big F of x is equal to the square root of 2x squared plus 3. So we're going to break it up again. I realize I already did this, but just for practice, let f of x, pardon me, not f of x, f of u, let f of u equal the square root of u. And let g of x equal u, which is equal to 2x squared plus 3. If we do that, then the derivative of f of u is equal to the derivative with respect to u of u to the power of 1/2, which, using our math knowledge, is the same as 1/2 u to the negative 1/2, or 1 over 2 times the square root of u. And the derivative of g with respect to x, or the derivative of u, is equal to d by dx, or d over dx, of 2x squared plus 3, or, remembering our rules, 2 times 2 is 4, x to the 2 minus 1, which is just 1, plus, well, 3 does not have an x next to it, so the derivative of that is 0. So now we have our two derivatives there. So we multiply them together. We know that dy d by dx, dy by dx is equal to the derivative of y the derivative of y with respect to u, multiplied by the derivative of u with respect to x, which we've already found. So that's equal to 1 over 2 times the square root of u multiplied by 4x. But we're not done yet, because that's not super useful. We don't want everything in terms of u, we want everything in terms of x. So first of all, I'm just going to combine that, so I'm left with 2x over the square root of u. And then finally, to get my answer, I'm going to substitute in my value of u. So my value of u, so 2x divided by the square root of my original u, which is 2x squared plus 3. 2x squared plus 3, which is my answer. So the derivative of big F of x is equal to 2x divided by the square root of 2x squared plus 3. So that's example number 1. Let's move right along. So example number 2. If y is equal to u to the power of 10 plus u to the power of 5 plus 2, and u is equal to 1 minus 3x squared, find the derivative of y with respect to x at the point x equals 1. So let's use our Leibniz notation once again. dy by dx is equal to dy by du multiplied by du over dx. So, taking the derivative of our first part, using our rules, we have the derivative of u to the power of 10 is equal to 10 times u to the power of 9. And then u to the power of 5 is 5 times u to the power of 4. And the derivative of 2 is 0. So we leave that with that. And then the derivative of u with respect to x is very similar. The derivative of 1 is 0. The derivative of negative 3x squared is negative 3 times 2, which is negative 6, multiplied by x minus 1, or x squared minus 1, which is just plain old x. Now, right here, looking at this is pretty scary because we know that u is equal to 1 minus 3x squared, and then substituting that in and taking it to the power of 9 and multiplying it by, it's going to be a mess. But luckily we were given a specific point when x is equal to 1. So because of that, we can just substitute that into our u and use that value to substitute into our equation here. So little aside over here, u at the point 1 is equal to 1 minus 3 times 1 squared, which is equal to 1 minus 3, or negative 2. Great. That's a lot easier to deal with. So we have 10 multiplied by negative 2 to the power of 9 plus 5 multiplied by negative 2 to the power of 4, all multiplied by negative 6x. So, putting that in your calculator, unless you're feeling rather clever. So 10 multiplied by negative 2 to the power of 9 is going to give me the value of negative 5,120 plus, I'll just do separate brackets here, 5 times negative 2 to the power of 4. That one's not so bad, so 5 times 16, which is going to give me 80, all multiplied by negative 6x. And I can simplify before or after. And actually, sorry, we know the point x, so let's put that in now. X is equal to 1, so it's all just multiplied by negative 6. So we have negative 5,120 plus 80 multiplied by negative 6, which is going to give us a final answer of 30,240. So using my chain rule, I took a very daunting looking example and was able to find the solution. Luckily, we were given the point x equals 1. That made life a lot easier. But since Math 31 is meant to be done without a calculator, you can be pretty sure most of the time the numbers aren't going to be so bad. Okay. Now, I did mention earlier how we used the chain rule. I guess we didn't call it the chain rule then, but when we had perfect squares and perfect cubes and such, we were using a form of the chain rule to solve the answer, and that we would be learning today how to do that with any power. So that's what we're going to be doing now. And so this is the power rule combined with the chain rule. So we had the power rule before, and now we're adding the chain rule with it. And once again, the proof is in the book. We're not going to be dealing with that. I will just be giving you the rule. So the derivative with respect to x of a function u to the power of n, where n is any real number, and u is equal to a function g of x and is differentiable, so basically anything we're going to be dealing with, is equal to n multiplied by u times n to the power of, or n minus 1 to the power of n minus 1, which you guys know already, multiplied by the derivative of u with respect to x, du dx. And I guess we can write it in a slightly different form if we just want to call it g of x. So g of x to the power of n is equal to n times g of x to the power of n minus 1, multiplied by the derivative of g of x, g prime x. So with that information, we can move on to example number 3. Example number 3 asks, if y is equal to x squared minus x plus 2 all to the power of 8, what is the derivative of y with respect to x? Well, we're going to be exploiting our power rule combined with our chain rule to figure this one out. So we will let u equal our function g of x, which is x squared minus x plus 2. And we're going to let n equal 8 because it's all to the power of 8. Then using our rules, we know that the function y with respect to x is equal to, according to our rule, our n, so 8, multiplied by our function u, x squared minus x plus 2, all to the power of n minus 1, which is 7, or all to the power of 7, multiplied by the derivative of that function u with respect to x. So x squared minus x plus 2. Well, that's an easy enough one to do using our addition rules. So I'll rewrite what I have there. X squared minus x plus 2 to the power of 7. And then I will take the derivative. Well, the derivative of x squared is simply x, minus the derivative of x, which is just plain old 1, plus the derivative of 2, which is 0. So I am left, 2x, not just x, 2 times 1, which is 2x minus 1. So I'm left with my answer. The derivative of the function y with respect to x is equal to 8 multiplied by x squared minus x plus 2, all to the power of 7, multiplied by 2x minus 1. And so that is the answer to example number 3. All right, so let's move on to example number 4. Example number 4 says, let me just write it up here. Oh, there we go. That's a 4. 4. Find f prime x if f of x is equal to 1 over the cubed root of 1 minus x to the power of 4. So 1 over the cubed root of 1 minus x to the power of 4. So first of all, we're going to rewrite this function, make things just a little easier. So that is the same as 1 minus x to the power of 4, all to the power of negative 1/3. So using our rules, our chain rule combined with our power rule. Sorry about that. Misplaced my notes for a second there. Chain rule mixed with power rule. We do know that the derivative of f is equal to n, which in this case is negative 1/3, multiplied by our u, which is 1 minus x to the power of 4 to the power of n minus 1. Now, n minus 1 is the same as negative 1/3 minus 3/3, or negative 4 over 3, multiplied by our u, which in this case, the derivative of u, or the derivative of our inside function, which is the derivative of 1 minus x to the power of 4. Well, the derivative of 1 is 0. And negative x to the power of 4, the derivative of that is negative 4 times x to the power of 3. So we have that right there, and we can rewrite it once again. So we have a negative multiplied by a negative, which makes it a positive. We have this value to the power of negative 4/3, which is the same as 1 over. Now let me just rewrite it. So this stays on the top. We have 4x to the power of 3 divided by 3 multiplied by 1 minus x to the power of 4 to the negative 4/3, or to the 4/3, which we could write as 1 minus x to the power of 4, all to the power of 4, underneath a cubed root. In the textbook, they just leave that to the power of 4/3, and that might be easier. Either way, we have here our answer. Example number 5 asks us to differentiate s, where s is equal to 2t minus 1 over t plus 2, all to the power of 6. So now we not only have to combine the power rule and the chain rule, but we also have to throw in the quotient rule. So things are going to get a little bit messy, but we'll take it one step at a time. So let's just start using our chain rule, our power rule, chain rule combined. So we have the derivative of s with respect to t is equal to, and you know what, why don't I will write this, so I don't forget, let n equal 6. Let g of x equal 2t minus 1 over t plus 2. So we have the derivative of s with respect to t is equal to n, which is 6, multiplied by g of x, which is 2t minus 1 over t plus 2, all to the power of n minus 1, or 5, multiplied by the derivative of g, or sorry, this should be g of t, not g of x, because our variable is t in this case. So the derivative with respect to t of our g, so 2t minus 1 over t plus 2. Sorry, I got a little excited there when I wrote it. So we have the first part of our answer, no problem. The second part, we're going to have to use our quotient rule to deal with that. So using our quotient rule, let's say f has not been used, so we'll say let f of t equal 2t minus 1. Let g of t, no, we've already used g, pardon me. Let h of t equal t plus 2. Then the derivative of f to the power of t is equal to 2, and the derivative of h with respect to t is equal to 1. Okay, now we're ready to do our quotient rule. So, we have ds with respect to t is equal to, just copy the first part down, 2t minus 1 over t plus 2, all to the power of 5. And then we're going to multiply it by our derivative. So if you remember our quotient rule, it is g times the derivative of f minus f times the derivative of g. So in this case, we have t plus 2 multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom. I should have just been calling them top and bottom the whole time. The derivative of the bottom is 1. Divided by the bottom squared. So this looks very messy indeed. But it does simplify somewhat. So the derivative of my function s with respect to t is equal to, I'm going to draw the top slightly different from the bottom for now. So that is the same as 2t minus 1 to the power of 5 divided by t plus 2 to the power of 5 multiplied by, well, our top here, we have 2t plus 2, 2t plus, 4, minus 2t minus 1, which is the same as plus negative 2t plus 1, divided by t plus 2 squared. Well, how convenient. Our bottoms are exactly the same. And you know what? I bet if I fool around with the top, we're going to get something similar as well. So let me just switch to a red pen so we can do some cancellations here. So we have 2t and negative 2t, so they cancel each other out. And we're left with just 5. And then the bottom, well, the bottom is still the bottom. So rewriting that once again, we have the derivative of x with respect to t is equal to 6 times 2t minus 1 to the power of 5 over t plus 2 to the power of 5 multiplied by 5 over t plus 2 to the power of 2. Now I have t plus 2 to the power of 5 multiplied by t plus 2 to the power of 2. Remembering my rules from earlier math classes, I can just add those exponents together, and on the bottom I'll have t plus 2 to the power of 7. On the top here I can multiply everything together, so 6 times 5 gives me 30. And then multiplied by 2t minus 1 to the power of 5 divided by t plus 2 to the power of 7, which gives me my answer. I've now combined my power rule, my chain rule, and my quotient rule to get the answer to example number 5. Example number 6 asks us to find the derivative of the function f of x is equal to, I should write this, so example number 6, f of x is equal to x squared plus 1, all cubed, multiplied by 2 minus 3x, all to the power of 4. So we're going to use our product rule before we use our chain rule. It can be really easy to get lost with a question like this, and so I'm going to make a few definitions first. So I will say, and since I have room over here, and I'm afraid I might run out of room, I'm going to actually start it over here. Come on, mouse. Come on, mouse. So starting over here, we will say g equal x squared plus 1. Let h equal 2 minus 3x. We'll find the derivatives. Then the derivative of g is equal, with respect to x, of course, is equal to 2x. And the derivative of h, with respect to x, is negative 3. We will define our function I equal g to the power of 3. And h equal, or pardon me, not h, j equal h to the power of 4. So we will let j equal h to the power of 4. So that way we can do our chain rule and our quotient rule, no problem. And I guess we should write our derivatives. It's equal to 3 according to our power rule. 3 times g to the power of 2 multiplied by the derivative of g. And j, the derivative of j, would be equal to 4 times h to the power of 3 multiplied by the derivative of h. I realize this is a lot of stuff, and that's one of the nice things about having this recording. You can stop and go back, and of course you can always ask me questions after you've watched it if you have any questions. So we're going to rewrite our question here completely. We're just going to rewrite it, first of all, as a product rule question. So we have f of x is equal to I multiplied by j. Because that's what we have. We have I is equal to the g to the power of 3, and g is equal to x squared plus 1. So x squared plus 1 to the power of 3 is equal to I. And same for j. Using our product rule, we know that the derivative of x is equal to, the derivative of f is equal to I times the derivative of j plus j times the derivative of I. So I can now substitute in my information. So I is equal to g to the power of 3, and the derivative of j is equal to 4h to the power of 3 multiplied by the derivative of h plus j, which is h to the power of 4, multiplied by the derivative of I, which is 3 times g to the power of 2, multiplied by g, or the derivative of g. I now substitute in my values for g and h, because everything now is just in terms of g and h, so, and g prime and h prime, which we already have. So that is equal to x squared plus 1 to the power of 3 multiplied by 4 times my h, which is 2 minus 3x to the power of 3, multiplied by my derivative of h, which is negative 3, plus h to the power of 4, so my h is 2 minus 3 times x to the power of 4, multiplied by 3 times g to the power of 2, so x squared plus 1 to the power of 2, multiplied by the derivative of g, 2x. Now, if you look in the book, they did this in a very different manner, or they got to this step in a very different manner. I like to break it up. I think it's way easier to avoid mistakes when you break it up like this, even though it might be slightly tedious to write all of those new variables out. So given this, when we multiply it all out, we find that our function x is equal to, well, 4 times negative 3 gives me negative 12, multiplied by x squared plus 1 to the power of 3, and 2 minus 3x to the power of 3, plus 3 times 2x, which gives me 6x, multiplied by 2 minus 3x to the power of 4. I actually wanted to do it in the other order, but it doesn't matter in the end. Multiplied by x squared plus 1 to the power of 2. Finally, this isn't a necessary step, but it's a good step to do. I look for common factors. So I have a negative 12, positive 6. I have x squared plus 1 and 2 minus 3x in all of my terms. So I am going to be taking out a factor, negative 6. And then my greatest common factor is going to be x squared plus 1 to the power of 2. So x squared plus 1 to the power of 2. And my greatest common factor of the other one is 2 minus 3x to the power of 3. And then I put back in what I have left. So negative 12 divided by negative 6 gives me 2. X squared plus 1 to the power of 3 divided by x squared plus 1 to the power of 2 leaves me with a single x squared plus 1. 2 minus 3x to the power of 3 divided by 2 minus 3x to the power of 3 gives me just plain old 1, plus 6 divided by negative 6 gives me negative 1. It was a 6x, so 6x divided by negative 6 gives me negative 1x, or negative x. 2 minus 3x to the power of 4 divided by 2 minus 3x to the power of 3 leaves me with a single 2 minus 3x. And then finally, x squared plus 1 to the power of 2 divided by x squared plus 1 to the power of 2 leaves me with 1. And after I sort that all out, I have my final function negative 6 times x squared plus 1 all squared multiplied by 2 minus 3x cubed multiplied by, so we have 2x squared plus 2 minus 2x plus 3x, which comes together to give us positive 5x minus 2x and left over with a 2. And there we go. Yeah. So that's it. That is the final answer. This one's a doozy. Like I said, they get ridiculous. And the last example, or the last two examples, are no exception. Actually, example number 7 isn't too bad. It's more of a theoretical example, so that's where we are going to next. So example number 7 gives us two things. It says if h is a differentiable function, find the derivatives of the following functions. So big F of x is equal to the function h of x all cubed. And so that's A. And then for B, we have g of x, big G of x, is equal to h multiplied by x cubed. And so we have to find the derivatives of both of these using the chain rule. So for A, we are going to say, let u be equal to h of x. And because of that, y is equal to u cubed. So using our chain rule, we know that big F of x is equal to derivative with respect to x of our function h of x cubed, which is equal to the derivative of that guy. So dy by du multiplied by du dx. So the derivative of y with respect to u is 3 multiplied by u squared. And the derivative of u with respect to x, well, we're not given what u actually is. We're just given the function h of x. So it's just going to be our h prime, or h of x prime, because we don't know what that derivative is. And so substituting back in that u, we find that the derivative of big F of x, forgot my derivative sign over there, is equal to 3 multiplied by h of x squared multiplied by the derivative of h. And that's our answer. That's as far as we can go with that, because we don't have an actual value for the function h of x. For our b, we are going to be doing things a little bit differently, because this time we have our h as the outer function, and the x cubed is the inner function. So I'm going to first define g of x. So let g of x equal x cubed. And then we will just use our first definition, or no, it wasn't the first definition, I think it was the second I gave you, but we will use our other definition of the chain rule, the non-Leibniz notation, to solve this one. So, according to the non-Leibniz definition of the chain rule, the h of g, in this case, so the hog, the derivative of our hog, so h of g of x, is equal to the derivative of h of g of x multiplied by the derivative of g of x. So let me even write up here. So we are doing hog h of g of x. So the derivative in this case is going to equal derivative with respect to x, substituting in our values that we have, equal to h prime, and our g of x we've already determined as x cubed, multiplied by our derivative of g of x, which, well, the derivative of x cubed is equal to 3x squared. And that's it. That's it. We can rewrite it the same way that they wrote in the book. So we'll do 3x squared multiplied by the derivative of h x cubed. And that's example 7 right there. Finally, moving on. Let's move on to example number 8. Example number 8, this is where things get peak nuts. Because not only can you use the chain rule once, you can use the chain rule infinite amount of times. So we are going to deal with a chain rule of a chain rule. So a chain of a chain. So if y is equal to the square root of x plus the square root of x squared plus 1, what is the derivative of y? So yeah, things are going to get a little bit crazy. We are going to exploit our power rule, chain rule combination to solve this one. So I'll first of all rewrite this as x plus x squared plus 1 to the power of a half, all to the power of a half. And this is where I'm going to be using the ill-advised method of not giving everybody a little variable, not saying this is f, this is g, this is h, this is I. We're just going to try and do it without doing that. So first of all, we'll use our power rule chain rule for the outside. So a power rule chain rule of the outside lets us know that the derivative is n multiplied by the inside. So x plus 1 to the power of a half, x squared plus 1 to the power of half, multiplied, or all to the power of 1 half minus 1, so negative a half, multiplied by the derivative of the inside. So the inside, of course, is x plus x squared plus 1 to the power of a half. Okay, well, that's the first part done. We don't have to worry about this anymore. Now we have to move on to this one. We've finished our first chain. Time to move on to the second chain. So I'll rewrite what I have first. So 1 half x plus x squared plus 1 to the power of a half to the power of negative 1 half. And I think I might do it as they do in the book and rewrite that next time in fraction form. But let's move on to this part here. We're going to use our power and chain rule combination once again. So we are given Oh, I guess we're throwing in the addition rule too. As well as an addition rule. So first of all, we take the derivative of the first term. So the derivative of the first term is just 1. Hallelujah. So the derivative of x is just plain old 1. Plus, now the derivative of my second term, I'm going to be using my power chain rule. So my n is still 1/2, so I'll bring that down. Multiplied by x squared plus 1 to the power of 1/2 minus 1, or negative 1/2. And then I'm going to be multiplying it with the derivative of the inside, and the derivative of the inside is 2x. And there we go. Okay, now the fun part, trying to simplify. So I will rewrite this as a fraction as I said I was going to. I'll start with the bottom. So that's 2 times x plus the square root of x squared plus 1. And all of this is under an additional square root. Well, that was a funny looking square root, but that's what we're dealing with right now. Over 1. And we are multiplying it by 1 plus 2x, because we're multiplying 2x, over 2 times the square root of x squared plus 1. I've got 2 on the top, 2 on the bottom, so I can do a quick cancellation there. So I will cancel out my 2's. So I could rationalize the denominator of the second term and just, no, we're going to leave it there because that's perfectly acceptable. So as simple as we are going, 2 multiplied by the square root of x plus the square root of x squared plus 1. Multiplied by 1 plus x over the square root of x squared plus 1. And that's it. That's the chain rule. 8 huge examples of the chain rule. So just to recap, the chain rule is a way that we can find the derivative of functions that are embedded within functions. So functions within functions. There is a shortcut that we can use when those functions are power functions. And we use that, the combination power and chain rule. It takes a lot of work sometimes. It's often a good idea to use variables to replace portions of your functions to make it a little easier to work with bit by bit. But however you do it, as long as you do it right, you'll get the right answer. So there are a lot of ways to find the right answer. You find what works for you. And yeah. So hopefully this was helpful. If you have any questions, please do let me know. Reach out to me and I will try my best to help you out. Hope you have a great day, and I will talk to you later.